Welcome everyone to this CapTech presentation. Today we have a very special guest. His name is Carlos Cesio Garcia Mendez Mijares. He's a mechatronics engineer and a research intern at Harvard.
Thank you for inviting me, and thanks everybody for joining. Right. So let's get right into it. Right? As you know, the theme of today's presentation is going to be print your own bioprinter. Right. So we'll get into all those specifics. So basically, the agenda for today. First, we're going to do a little bit of an introduction. So I'll tell you guys a little bit about me, some of the research groups I've been involved in, the responsibilities that I have, or people with my background have in these research groups. From there, we're going to go into bioprinting, right? A brief introduction and the importance of bioprinting, the relevance of the DIY community in bioprinting, and then the important part, right? How to build a bioprinter and all that comes with it. We'll get into that later on. Some of the related projects I've done to bioprinting, right, with other technologies. And lastly, the experience I've had while at Harvard, right? And basically, to sum it up in one word, it's amazing. And I've said we'll get into all that. So let's start, right? A little bit about, right? So I'm a mechatronics engineering undergrad at Tecnológico de Monterrey, Campo Monterrey, right? This is my last semester before I graduate, hopefully, right? And I am also a research intern at the Alvarez Trujillo Biomedical Research Group, Tec de Monterrey, right? And I highly recommend this research group. It's filled with amazing people. You can see some of them, most of them in this picture. And it's led by two amazing doctors, right? Dr. Alvarez and Dr. Trujillo. So I highly recommend you guys to research more or investigate more about this group. It's great people. And thanks to this group, I was able to have the opportunity to join the Zhang Laboratory at Harvard Medical School and Brigham and Women's Hospital here in Boston. So that's a little bit of my background right now. So I'm a mechatronics engineering student and I'm in a bio world. So what exactly do I do? Right? Because I'm not with the biological stuff. Well, basically one of the responsibilities I have is to be in charge and handle some of the different equipments that we have, and that is like conventional 3D printers, different types of printers such as SLA and DLP, also laser cutters. Here you see me, I was in charge of the installation and usage and maintenance and all that of the laser cutter that we have at Tec de Monterrey. So that's some of the things I'm involved in, right? And to sum it up with one word, oversimplification of things, I have to fix it. I have to figure out how to fix it. But basically, what we really do, right? What we really try to do as mechatronics engineers in this group, in these groups, is create innovative and cost-effective solutions. That's really what we're trying to do, right? And the way that we do this is by designing, right? It's a lot of CAD. SolidWorks is basically most of what I do, and you guys will see that in the presentation. Also a little bit of Blender, that's to modify STLs, and I've been using that a lot recently. A little bit of programming, you know, we program some Raspberry Pis, and obviously that's with Python, or we program some Arduinos, that's with C and C++, right? And we make some GUIs, which are user interfaces for the Arduino, and that's done with processing, right? And that's based off Java, right? You code that in Java. We also have to do some of the electronics, and to give an oversimplification, once again, it's basically you create a circuit with stepper motors. That's most of the circuits that we have to design are of that difficulty. However, one of the projects that we have right now, we have a heater, a 3x3 heater. So when you have 9 different pixels in that heater bed, and you have to control the heat at each pixel individually. So for that, we're going to use a digital potentiometer, and we have to do, that's mostly based off circuits, right? But that's one project. For the most part, we just do simple motor control, right? The voltage, a driver, and the microcontrollers, things like that. And also a lot of what I do is G-code generation. So if you sum all of these things that I just mentioned into one project, that's basically building a bioprinter, right? If you sum these skills, you can build your own bioprinter. So let's get into it, right? What is bioprinting? Well, bioprinting, again, this is going to be from a mechatronics viewpoint, not so much from a biological viewpoint. So it's an additive manufacturing technology in which cells are printed to create various constructs for tissue reconstruction, right? And how do you do this, right? How do you print the cells? Well, you can use different types of technologies. You have droplet and all the subdivisions in droplet. You have photocurin based, once again, all the subdivisions, and you have extrusion, right? So let's look at droplet, right? These are some of the types of technology, droplet-based technologies that we have. We have acoustic, one of them. We also have inkjet, and this was one of the printers developed by researchers at Oxford University, right? And they use droplet-based bioprinting. And then we also have, as I mentioned, photocurin-based, and that's basically you use a light source, right? I think this picture got flipped, so it's gonna be kind of hard to see it, but basically you can get it here, right? You have a light source at the bottom, and your stage starts moving up. Or you could also have it inverse. You have the light source at the top, and then your stage starts moving down, right? So you cross-link one layer, then your stage moves down. Cross-link the next layer, stage moves down, right? You create slices, 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 slices. Pretty straightforward. And then the technology that we're going to be focusing on today is extrusion based, right? This is the most popular technology nowadays. And this is a very, very famous printer in the DIY community done by Carnegie Mellon researchers, right? And specifically within all the types of extrusion based technology, we're going to be focusing on this one, right? Mechanical extrusion with force, right? Not rotation, with force. So let's get into how to build this specific type of bioprinter technology, right? So what is the importance of bioprinter? Now we know what is bioprinting. Why do we need bioprinting, right? So on average, 17 people die every day waiting for an organ transplant. And this is just in the US alone. And then even more astonishing, every 9 minutes, a person is added to the waiting list for an organ transplant. And if they do get an organ, and here you can see the amount of patients versus how many transplants were actually done. It's just, these numbers are crazy. They're ridiculous, right? And if they are able to achieve a transplant, look at the cost, right? $1.4 million for a heart transplant. That's a lot of money, right? Not everybody can pay that. So what bioprinting or bioprinters try to do is they aim to create artificial organs, right? That is why we are trying to develop bioprinters in an oversimplified way. So yeah, we're obviously still very far off. That is the end goal, and we're still at the beginning. But in order to reach that end goal, well, more research has to be done, right? So that means more research centers, more labs. They have to do more tests in order to have more information, more data, and get this bridge the gap between what we have and the end goal. And how do you do this? Well, you need bioprinters, right? And commercial bioprinters, as you see in this photo, they can cost, this one specifically can cost more than $200,000, right? So realistically, how many research labs have access to this type of equipment, right? Not that many. So the more people can use bioprinters and the more minds are collaborating together, the closer or the faster you'll be into reaching that end goal, right? Because you have more people. Everybody knows 2 minds is better than 1, 10 minds is better than 2, and so on and so forth, right? So that's where the DIY community comes in. So we're trying to make these systems affordable to the majority of people so more advances can be done. So this system specifically, which I developed in collaboration with some of my lab colleagues here at Harvard Medical School, it costs around $259, right? The minimum price. And that's 772 times less than the commercial printer I just showed you, right? So this is way more accessible to labs. Basically, anybody can buy this printer and do some experiments. You can do 772 times more experiments than if you just had one commercial bioprinter, right? Other issues come into question, like resolution, so on and so forth, other features. But as a basis, this is a great starting block, right? So now let's see specifically how to make this printer that you see in the picture. Okay, so we're gonna start with the framework. And what is the frame? Well, it's a 3D printer, right? And And why do we use 3D printer? Because it operates under the same instructions. You could also use many CNC machines like laser cutters, laser engravers, right? But a 3D printer is fairly simple. There's many easily available, economically speaking, 3D printers, right? And many of the components can be reused. As you see mentioned, stepper motors, the motherboard, power supply, the firmware is very similar. And if you get creative, you can even reuse the extruder as a heat bed, right? So for this specific presentation, we're going to be using the Ender 3 Pro as the framework, okay? So we now have the main part. So now let's start making some changes. And this, once again, is the Ender 3 Pro. So what are we gonna change, mechanically speaking, to this printer in order to get a bioprinter? Well, mechanically speaking, it's very simple. We just had to change these two things, right? And basically how you do that is you just create an extruder. So as you see before, there was one motor. I'm gonna go back one picture. So this motor, right, you're gonna remove this block, which is the heat block, and then you're gonna use this motor as the extrusion motor, right? And basically, once you create the CAD and you print all the pieces, the ones in color are printed, right? This you can print, but you buy, and this lead screw you also buy. But everything else on top, everything else is printed, and you reuse the same motor, right? You print all the pieces. You already have your extruder, right? That's the hardest part of the whole process, and we're already done with it, right? So from here on out, it's going to be downhill. What's the next step? Okay, the next step is the firmware. So we have to modify the firmware a little bit, and with that, we have to make sure we have some things before. So first, we need to make sure that we have the bootloader and it's been uploaded to our motherboard. And for that, when using the Ender 3 Pro specifically, we have to check what version of the Ender 3 board we have, whether it's version 1 or version 2, because version 2 already comes with the bootloader pre-installed, right? We just check what type of motherboard we have, and then from there we download Visual Studio Code. We add some extensions, which are these two, Platform IO IDE and Auto Build Marlin. We download Marlin from GitHub, right? And then there's a separate repository which has all the configuration files, right? You copy these files and you paste them into Marlin, right? All very simple up to here. And then you just modify Marlin, right? And this is the only difference between a regular firmware used for 3D printers and a bioprinter firmware as of right now, right? This modification. And how do we modify it? Well, it's really actually relatively easy. You just have to modify a couple lines. For example, this one, if you don't want to extrude with very high temperature and you want to be able to extrude when the temperature is 0, you have to change this value, right? And you make it equal to 0. Or you can just comment these lines as well. And also, if you want to be able to print at one point many millimeters, right? If you haven't calibrated your E steps correctly, then you also have to change this value, make it very high in order for it to let you print a G-code command in which your extrusion rate was very high, okay? Couple other lines that you can also change is your max feed rate, how fast you move, whether it's an X, Y, Z, or the extruder, how fast it moves, and also the acceleration, right? So those are a couple things that you can change if you want the extruder to be able to print faster, right? Spin faster, then this is one that you would need to change, 25. And if from the final speed to where you start, you wanted to reach that final speed faster, then this is the one that you would change, this 1000, right? Okay, and there's other lines that you can modify, right? You can modify your startup screen. You can enable mesh bed leveling. You can change the name of the printer and things like that, right? But as a general overview, with modifying what I just showed you, these 4 lines, you already have a simplistic view of your Marlin biofirmware, right? So once you have this, you build it and you upload it to your motherboard, and all the firmware is done, right? So now we have done mechanical and we've done all the firmware. So we're basically done. From here, if you want, you can change, you can also modify the electronics, right? So the Ender 3 specifically comes with this one. This is the stock board. And you can see it has, like, for the X-axis motor, the Y-axis motor, but you can upgrade it to the SKR, right? And this has silent drivers. So if it bothers you, if the printer is making too much noise, then you can use this. Or you could also upgrade to the Duet, right? And this one has with Wi-Fi included. Obviously, these upgrades do cost money, right? So if you want to keep it as inexpensive as possible, then you would remain with stock. And that's what we've done. And so far, it's been working great. If you wanted to add additional extruders, right, 2, 3, 4, then you would need to upgrade to something like the Duet and with the Duet extender, right? Okay, so now we have our printer. We finally finished it. Now let's get, how do we print, right? So printing is all G code. And here's an example of a G code that I had to generate. It's a simplified version of the Harvard logo. And the way, basically, there's way more commands to G code. There's over 100 commands of G code, I believe. But basically, to sum it up, I really only use, I think 3, right? G1, G2, and G3. G1 is linear, G2 is an arc clockwise, and G3 is an arc counterclockwise. And with those 3 commands, as you see right here, is actually only 2 commands, G1 and G2. And from there, it's just coordinate system. From this point to this point, what's the difference? And it's just X and Y and Z, right? That's all very, very simple. And you have to be able to create your own G code, modify G codes, and things like that. But this is fairly straightforward. What's the importance of modifying G codes? Well, you need to be able to play with the flow rate and the feed rate, right? Because these parameters, if you start messing around with them, you'll be able to have different resolution of your filament, right? You might want a very thin fiber. Well, then if you want a very thin fiber, you need to extrude, right? Your flow rate needs to be relatively low, and your feed rate, how fast you move from one point to another point, needs to be high. And if you want a very thick fiber, right, you need to extrude very much, which is what we're gonna see in this last line. You need to extrude a lot, and you need to move very, very slow. So as you see, the filament, right, the red material is coming out very slow, and we're very fast, sorry, and we're moving very slow. So that allows you to create a thicker fiber, right? So you mess around with these parameters in order to get the diameter you want, the resolution you want. And basically now you can start printing, right? So let's start printing. So this is an example of one of the prints that we've been doing here. This is, you have this solution, right, in which you print inside your solution, and that's called like suspended bioprinting. And you eventually are gonna remove your material, right? And you're gonna have this empty spiral inside your medium, and that's called sacrificial bioprinting, right? And what I was explaining before, if you mess around or if you play around with the parameters of feed rate, right, and flow rate, then you can get this matrix of parameters, right? This is a very high, very high flow rate and a very low feed rate, right? So that's why we get this thick square. And this is a very low feed rate and a very high feed rate and a very low flow rate, right? So that's why we get this thicker line, thinner line. Sorry about that. Perfect. So also, the one thing that I want to mention when we're testing and printing is that as of right now, bioprinting is it's more of an art than of a science. At least you have to look at it sometimes that way, right? There's going to be many times in which the prints just aren't good and you don't get a good quality of print. And you're going to be very frustrated. For example, in this image specifically, this is not what we wanted to achieve with the print, right? This is not how it's supposed to be, but still it looks amazing, right? It looks pretty cool. So you have to look at it more as an art, and eventually you will get there, and you just have to play around with it. Don't look at it so scientifically. Have fun with the whole process, right? So now that's basically, with all of this information, you guys are ready to create your own extrusion-based bioprinter, right? As you guys saw, it's fairly simple, right? So now let's get into projects that are related to bioprinting, and we're going to talk about different technologies. So the first one is DLP, right? So what is DLP? I mentioned this before, right? So basically, you're going to have your light source system at the bottom, right? It's going to go through this lens, and then it's going to be projected onto this platform. And from here, you have your stage, which moves up. right? So basically here, you're printing layer by layer. So the light source is activated, you print on this layer, light source turns off, and then you move a little bit up. Then light source comes up, you print on the next layer, light source off, then you move more up, right? So you keep going up, up, up. If the light source is at the bottom, if this was reversed, it'd be the opposite. Light source at the top, and you move down, 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 right? So this is digital light processing, bioprinting, right? And then another one, which is very, very awesome, is volumetric bioprinting. Now, this is a really new technology, and it's been developed by researchers at UC Berkeley, if I'm not mistaken, and they call this CAL. And the way it works, oh man, you could really get into detail. You could have a whole presentation just about volumetric bioprinting. It's amazing. It basically is like a CT scan, right? With a CT scan, if I'm not mistaken, you have your projections, right? And you have an object, and what you're trying to do is you're trying to create an image from that object, right? That's how CT scan, the concept works. And here it's a little bit different. You have your projection angles, you have your image, and what you're trying to do is you're trying to create your object, right? From these images that you're projecting as the stage is rotating. So what is my responsibility in this project that we're developing here? Our version of this project is upgrading or trying to change this stage system. So that's what you see here on the right. So that's why this is going to be all fully motorized. Once again, with the Arduino, a little bit of programming, the graphical interface with processing and all that. So that's kind of our version of what Cal has developed. And then lastly, let's get into the experience that I've had here while doing my research. So as I mentioned, to sum it in one word, it's been amazing, right? And why has it been amazing? Well, first and foremost, the people. One of the things that when I was talking to somebody, they told me that they loved about here, and it's very true. It's here and in many places with great people, they teach you, or rather, you learn how to learn, right? And that's very important. You learn how to learn. Also, the people here, they're very competitive, right? I mean, that's why they are where they are, but they also help you, right? They also want you to succeed, right? Everybody helps each other and pushes each other to be better. And that goes into the next point. It's a constant challenge. I mean, you always have to be on top of your game. You always have to be working. These guys, you come here Saturday, they're here working Saturday. You come here Sunday, they're here working Sunday. I mean, everybody's constantly trying to get better. And if you stay behind, you're going to be behind. It's that simple. Another reason why I love this experience is because of the environment, right? Specifically the city. Like, there's a bunch of great people here. You talk to a random person and, oh, what are you doing? Oh, I'm doing a master's in artificial intelligence. You're like, wow, that's absolutely amazing. And lastly, the lab, right? And what's great about the lab is the technology and the new ideas that you get to see every day at the lab. And I want to mention here in the technology side, right? Because I've been talking a lot about, oh, Harvard. A lot of the technology that has been developed here has been done by tech students, right? Tecnológico de Monterrey students. So really, as a university, I think we are very prepared, right? Because you look at a lot of these printers, they've been done by our fellow classmates, right? So we do have the capacity and we can make it here because I've seen it. I've seen guys succeed and be some of the best here. So we can do it, that's for sure. And my last advice, just go for it, right? If you want to do it, just do it. You never know until you try, right? And that's a little bit on the motivational side, but yeah, go ahead. So thank you for listening, and that's the end of the presentation.